Hello, I'm David. It's semester 1, 2025, and this is a revision seminar for Maths 1B. And I've had some requests. So the people who are in the room have asked for these. This one was already on the board in the Maths Learning Centre. So cool. I will get on to that. So just a reminder, this is your seminar, so feel free to interrupt me if you have a question. You are allowed to do that. And I'll put I know that it's a bit loud, but it means that the microphone will pick it up. So, okay. So I might begin with the term. Oh, maybe I'll wait, because either of you didn't write this in the Maths Learning Centre? Did one of you write it? No? Okay. Well, I might wait and do that, because that person might turn up later. It'd be good for them to be here. But if I get through everything else and then they're still not here, I'll talk about it anyway. Okay. So I had a question about series, limits, and guesses for particular solutions for DEs. I might do them in the reverse order. So in this course, there's a section on second order linear differential equations. One of the ways of solving a second order linear differential equation is to find solutions to the homogeneous equation and then find one particular solution to the original and then add them together. So this is the idea. So you have y, ay double dash plus by dash plus cy equals some function like this. This is a classic second order differential equation with constant coefficients. Second order ordinary differential equation. Oh, not even linear differential equation with constant coefficients. That's the kind that it is. It's second order because there's a y double dash. It's linear because all of the derivatives and the original function are only multiplied by things. They're not multiplied by each other. And the constant coefficients is saying that these coefficients here are constants because it is possible for them to be functions. And you've seen first order linear ones where there's a function in this spot, but the second order ones you've only had constants in those spots. If you do a future differential equations course in your degree, there will be ones with not constants in these spots. But that'll happen if you do more differential equations in the future. And the system that you use is step 1 is you solve the homogeneous equation, which is a different equation, but it looks almost the same, except it has a 0 in this spot. And the way that you solve the homogeneous equation is you find two solutions, and then all the other solutions are, a times this plus b times this, so a linear combination. So for a and those two solutions are usually found using the characteristic equation. And then make all linear combinations. So it'll be A times something plus B times something, something like that. That's how it's done. That's how you solve the homogeneous one. So A times one of the solutions plus B times the other one, whatever's in those spots, you get them from back here from the characteristics equation. And that's, come in a bit closer. And then step 2 is you think of one particular solution to the original equation. And the way that you do that is normally you try y equals something with unknown coefficients. And then you sub that in to find the coefficients. Okay. And then step 3 is to add them together. I will get, so this will be y equals, I'm just going to do something like that. All solutions are the particular one you found plus the one you found from the homogeneous one. So they'll look something like that. So you take whatever you get here and whatever you get here and you add them together. And that gives you all the other solutions. So that's the plan. Except there's a little detail here, which is that when you try something like this, you need to make sure that none of it is already part of this one. Because if it was part of this one, then when you put it through this side of the differential equation, it would come out to 0. And so you want it to actually come out to Rx, so you need to choose something else. And the way to choose something else is to multiply the thing you wanted by X. So that's the idea. So it's best to do with an example. So I'm going to not do the bit where you solve the homogeneous equation first, just so that I can focus on the bit you asked about, but I will do a full one. Is that all right? Give me a moment to think of one that actually has solutions that I can be aware of. Something like that. Okay. So we want to find, and I'm just going to say note y double dash minus 6y plus 5y equals 0 as solutions. That. This poor old, there we go. As those solutions. So if I wanted to find all the solutions to this one, I know that I just need to find a particular solution to this, and then I can add this on and it would be all the rest of the solutions. So what I need to do is find a particular solution, and I will try y equals, and the way that you choose is you have this thing and any function that appears in its derivatives. So I have sine of 2x, right? And if I differentiate that, I'll get 2 cos of 2x. And if I differentiate that again, I'll get back to sine of, 2x again. And so if I think about all the derivatives of this function, they're all numbers times cos x and sin x. So what I will try is something times cos x, cos 2x, and something times sine of 2x. That's what I'll try. I will think about this thing and think about all of its derivatives, and I will do those things, but with different coefficients. How do you feel about that? And the reason you need to do that is because you're going to have to differentiate it to sub it into here, and you need all the things that are in the derivative to appear there, or it might not work out. So now I'm going to sub it in. So this will be minus 2c sine of 2x. And this will be 2d cos of 2x. Y double dashed will be minus 4c cos of 2x. And this one will become a minus this time. Like that. And then what I really want is minus 6 lots of y dash. So I'll just figure that out. So that'll be 12c sine of 2x minus 12d cos of 2x. So just minus both of these by minus 6. And I need 5y as well. So that's 5c cos of 2x and 5d sine of 2x. And so these three things, when I add them together, are supposed to come out to sine of 2x. Because I have y dashed, which is here. I can't see them both at once, just a second. I have y dashed, which is here, minus 6y. Oh, whoops, that's just y dashed. Y double dash, which is here, minus 6 of y dash, which is here, and 5y, which is here. And so when I add all these things together, it's supposed to come out to sine x. So y double dash minus 6y dash plus 5y comes out to, let's see. So the cos of 2x, I've got minus 4c and minus 12d and plus 5c. So that's 5c minus 4c is c minus 12d. That's how many cos of 2x's I have. So that's these ones. And the sine of 2x's I have 5d minus 4d, which is d, and plus 12c sine of 2x. That's what happens when I add all of those things together. And this is supposed to work out to sine of 2x. Because the original function, when I put all of this in here, it's supposed to be equal to sine of 2x. So I'll put that in. And so now, cos of 2x and sine of 2x are independent functions. And so I can equate the coefficients. Or I can sub in values of x. Either way, whatever you think is best. Because you could sub in, for example, pi on 2, and that would make the sine 0. But it would make the cos negative 1. So you could put cos of 2 lots of pi on 2, that would be cos of pi, which is negative 1. And so that would give you an equation to solve as well. That's one way of dealing with it. But most people just equate the coefficients. So the coefficient of cos 2x is c minus 12d, which is supposed to be 0, because there's no cos 2x's over here. And so c is 12d. And the coefficient of sine 2x is d plus 12c, which is supposed to be 1 over here. But we already know that c is 12d, and so we get d plus 12 times 12d is 1. And so 145d is 1, and so d is 1 on 145. That's 12 times 12 is 144, isn't it? Yeah, okay. Which means that the c must be 12 on 145 because c is 12d. So I've gone through all this effort to find just one answer. And so it's very important at this point to put these things back into the original thing that you tried. This all came from trying this to start with. And so I've got 12 on 145 cos of 2x and 1 on 145 sine of 2x. That's the particular solution. Well, and so that's the particular solution, is a particular solution. And so therefore, if I add on the general solution, then I will get the general solution to the original. So this is the one that went with the homogeneous one. So I add that on, and that gives me the general solution. And the reason this works is that I know that if I put this through this process here with the y dashes and the y double dashes and the y dashes and calculate it all, it comes out to sine of 2x. But I also know that if I put these through that process, they'll come out to 0. And so if I add them together, this bit will come out to sine of 2x and this bit will come out to 0. So it will still come out to sine of 2x after all. And therefore, it's another solution. How do you feel about that process? Okay. I'm going to do the same differential equation, but with a different Rx. Okay? Yes, please do. Correct. So if you're saying that this was 0 to begin with, you would only have to do this and then you would stop. Correct. So because the particular solution for the one that comes out to 0 is y equals 0. So you don't have to talk about the particular solution when it's already homogeneous. That's what you're asking? Okay. I should put page numbers on this, or I'm going to use them. So I'd like to do 2 other examples, but I'm not going to change this bit, if that's okay. I'm just going to keep it the same. So what if that's a 7 e to the power of x? That's good. In that case, the homogeneous is the same because this part's the same. So here's the thing. So with the particular solution, I would try y equals this thing and any of its derivatives. But let me just think about this. The derivative of e to the x is still e to the x. And so I just have to have this, that's all. So I'll try something, maybe not an a because I already used a. Try this. That's what I would try. It looks like this thing, but it has a different constant. But the problem is that's already here in the homogeneous solution. Already in the homogeneous solution. So instead, I'll try x e to the x instead. That's it. Like, so if it's already in part of the homogeneous solution, then you multiply by x. And when I mean part of, I mean it's one of these 2 bits. So it would be totally okay if the homogeneous solution had like e to the x cos x. You could totally still have e to the x. That'd be okay. It doesn't matter if it's times by something else. If it's just there on its own, that's when it's the problem. So that's what I would have to do. And the reason I would have to do that, because I know is if I subbed this into here, it would come out to 0, because that's what the homogeneous solution says. And I don't want it to come out to 0. I want it to come out to 7e to the x. That's the issue. I just want to prove that to you. Ready? Ready? This is just an aside. If y was c e to the x, then y dash would be also c e to the x. Y double dash would be also c e to the x. And so therefore, y double dash minus 6y dash plus 5y would turn out to c e to the x minus 6c e to the x plus 5c e to the x. And I would get 1 minus 6 plus 5, which is 0 c e to the x, which is 0. And so it's never going to be 7e to the x the way I want it to, because it belonged to the homogeneous solution, and the homogeneous solution, when you put it through here, comes out to 0. It will never work. So that's just, you don't have to try that, but I just wanted to prove to you that it worked that way. Okay, so we're actually going to try that y is c e x e to the x. Y dashed is therefore product rule, so I'll differentiate that and keep that, and then I'll keep that and differentiate that, so I get this. That's not nice. And then I will do it again, I suppose. I guess this is c1 plus x e to the x. And so then y double dashed is differentiate that, which is just c, and keep the e to the x, and then keep this and differentiate the e to the x. Okay, so I get c2 plus x e to the x. Cool. Okay. And then what have we got? Minus 6 lots of y dashed is minus 6c1 plus x e to the x. And 5y is 5c x e to the x. And these three things added together should come out to 0. No, not 0. They should come out to 7e to the x. Okay. So the total y double dash minus 6y dash plus 5y. Our total has come out to, they've all got a c, right? No, that's bad. I'm just going to do it. I should have kept it out, expanded out, shouldn't I? Instead of factorized it. Because that's not pretty. I don't like it. But there is a c e to the x in all of them. And then I have a 2 plus x and a minus 6, 1 plus x, and a 5x. Yep. 2 plus x minus 6x plus 5x. Oh, look at that. That's neat. Excellent. They cancel each other out. And so I've got minus 4. C e to the x. And it's supposed to be 7e to the x. And so look at that. The x e to the x part kind of cancelled out, and I was left with just an e to the x to match up with the 7e to the x that was there. It's very convenient. Some people who have trod this path before us have learned that this is how it works. And so e to the x can't be 0, but I can also just equate coefficients. And so c is therefore minus 7/4. And so the particular solution is y equals minus 7/4 x e to the x. And therefore the general solution is y equals minus 7/4 x e to the x. plus a e to the 5x plus b e to the x, because that was the original homogeneous one. So the hardest part of doing this is actually making sure you don't lose any terms when you do the derivatives and sub them in. Some people like to sub them in one at a time here. I find it much easier to write them all down separately and then combine them after, but you can decide how to show your working. That's up to you. Okay, I'm not going to finish these ones, but I just want to show you how they might look. So, what if it was y double dashed minus 6x, not x y dashed is x squared? Then I would imagine x squared and its derivative is 2x and its derivative is 2 and its derivative is 0, right? So if I think about all the derivatives of x squared, I will try something x squared and something x and something that's a constant. And then after that, I don't have to add any more things. But you have to have all the derivatives. And even if it had been x squared plus 1, that's okay, because there's a constant as part of this and here, and so this covers both of them. That's all right. So this e covers both of these constants because they're both constants, so it's okay. Yeah. So just want to point that out, is that you don't, even if this already has an extra piece, you don't have to worry about including a constant for this and a constant for this. But I won't finish that. It'll work the same way. You'll do the derivatives, you'll sub them in, you'll equate the coefficients, and that'll give you what these coefficients are. And I have one more. What if it was this? Squared e to the x? Well, then I imagine all the derivatives of this, and that will eventually contain all the derivatives of this and all the derivatives of this. But let me think about it. X squared e to the x. I'd get a 2x e to the x and an x squared e to the x. I already know what the derivative of that bit is, so I don't have to worry about that part. And I'll get an 2 e to the x and an 2x e to the x. And then that's always just going to be 2 e to the x from that point forward. So I'm going to need to contain all of these things. I'm going to need to try y is something x squared e to the x and something times x e to the x and something times e to the x. Only I won't have to include this one because it's in the homogeneous solution. Which means you may, in fact, have to include an x cubed e to the x if it doesn't work. Because you might need 3 of them. I do not feel like doing this, but I would be most interested to find out whether I need to have an x cubed e to the x. Actually, I just want to see. Just want to see. I want to try something. Y dashed is differentiate this. And so that's 2ax and leave the e to the x and then keep the ax squared. Hello, welcome. and then differentiate this. Okay, and then y double dash is 2a. And this, we've already got that one, haven't we? And the derivative of this is b e to the x. Wow, that is some serious stuff. And so I'm going to need 5 minus 6 this. And 5 of this, aren't I? Oh no, don't do that, David, to yourself. I'm just going to do it properly, or I'll get it wrong. Minus 6a minus 6a squared x minus 6. Oh, there was a 2 there originally, wasn't there? Yes, there was. And then 5y is 5a squared x plus 5. So let me just have a look at this. These three things, when I add them together, are supposed to come out to x squared e to the x. So I've got ax squared e to the x and and ax squared e to the x there. Not there. So it's these three, sorry. So an ax squared e to the x there, and an ax squared e to the x there, and an ax squared e to the x there. Ah, crap. They all cancel out, don't they? Look, 1 minus 6 plus 5, they all cancelled out. And so I end up with no x squared e to the x's, but it's supposed to work out to x squared e to the x. So it completely failed. Oh, damn it. So there's 0 ax squared e to the x's. And so that's never going to be equal x squared e to the x, is it? Damn it. Okay, so I told you I was worried that I might need a whole extra one. I do. So it turns out, this is worth noting, it turns out if the last one is in the homogeneous solution, then you're going to have to multiply them all by x. Oh, that makes total sense. Okay, I just wanted to check. If the last one here is in the homogeneous solution, I'm going to have to multiply it by x, but that makes it the same as this one, so I have to multiply this one by x, and that makes it the same as this one, so I'm going to have to multiply this one by x. So what we should have done we should have done y equals ax squared e to the x plus bx e to the x plus c e to the x. But this one is in the homogeneous one, and so therefore we added an x here and an extra x here and an extra x there. And that's how we should have done it. Okay. Cool. And that will prevent this thing happening that happened there where the term that I really wanted to work out to be disappeared. And if I have the extra x here, it won't do that. Right. Well, I'm glad I did that. I was worried, and I wanted to show you that if you happen to do something wrong in the exam like that, then at least you can say, oh no, I should have gone back and done this. And even if you didn't have time in the exam to fix the problem, you could say, oh, what I should have done is this. And then at least you'll get one of the marks that you should have done. But before the exam, you can certainly just give things a go and see how it works out. And then it gives you ideas to say, oh, okay, well, that tells me that I should have tried this instead. Every time you get something wrong, it should give you an idea of something you should have tried instead. And then next time you can do it better. Plus, it's never a bad thing to practice your algebra. So do not consider this wasted. All right. Is that enough of that? Okay. So I will say this only works in this constant, this particular solution by trying something with unknown coefficients only works if this runs out of things in its derivative. So when you have e to the x, it's always the same, so there's no new things when you differentiate it. And when you have a power of x or a polynomial, you'll eventually get to 0, so you run out of new things. And sine and cos just keep producing each other. But if you had something like tan x in this spot, you wouldn't be able to do it, because tan x and its derivative is sec squared, and that derivative is and then that derivative is even worse. And so you never run out of derivatives. So you can't use this process for things where this continues to have new derivatives. And if you had like ln of x here, it still wouldn't work, because you get 1 over x, and then you get x to minus 2, and then you get x to minus 3. You'd never run out. So it tends to only work with polynomials and trig functions and exponentials. Yeah. If you have anything else, then you may have to learn a whole new way of thinking about. That's not in this course, so that's a okay. All right. You don't have to, Karim, you don't have to answer by speaking, but you can type something in the chat if you like. You didn't happen to be the person that wrote a request on the Maths Learning Centre whiteboard, did you? Like there was a request for determinants on the Maths Learning Centre whiteboard. Was that you who asked? Okay, worth checking. Okay, so I may talk about some of those limits. You said there were some specific ones that bothered you. Do you know any of them off the top of your head? I'll come have a look. All right, so not limits then. They are technically limits, but they are a series, and so that is a whole other thing. So that's fine. We won't talk about limits then. We may if we want to come back to it. But okay, we can talk about series. Series is one of the common requests for Maths 1B revision seminars. Most years someone asks about series. I say that to make you feel better, because everyone asks. That means you're not unusual. It's normal to ask about series. So a series is an infinite sum. There'll be some sort of expression here involving n, a thing with n in it. And it doesn't have to start at 1. It could start at 0. It could start at 10. Could be other numbers. But the important thing is that this is a sum that goes to infinity. So there's a definition of what that means. So I'm just going to traditionally call it an. It's technically a function of n, so you could write f brackets n, that would work as well, but it's traditionally called an. What this means It's defined to be the limit of this. A1 and A1 plus A2, and A1 plus A2 plus A3, and A1 plus A2 plus A3 plus A4, and so on forever. So it's the limit of the running total. I call it a running total, but the official word is the partial sums, just in case you were wondering. So that's the definition of what it is, but almost never do you actually use that definition. It's very rare to use that definition. There is one proof in this course that I know of that uses that definition. Yeah, mostly you just think that that's what it is, but you don't use that fact. But that is what it means. That's the definition. And so, therefore, it seems the first theorem of series is that if these individual little bits don't get any smaller as you go forward, then it's not going to add up to something. Because if you just keep adding 1 over and over and over and over, you'll just get infinity. And if you keep adding, you know, 1/100th over and over and over, you'll still eventually get to infinity. It'll just take a little longer. So if these individual things don't get smaller as you go along, it won't work. Yeah. So there are many, many things that you can imagine putting in this spot that will not add up to anything. And when we say it has a limit, what that means is, so when it does have a limit, we say that this converges. So if it has an answer, which means that this has a limit, we say it converges. That's what we say. And the big question is, if you think of a random function to put in this spot, how do you tell whether it converges or not? That's the big question. And even better, can you even figure out what the total is going to be? Can you figure out what the sum will have an answer of? That's the question. And knowing whether it converges is a little easier than finding what the sum actually is. But knowing whether it converges is sometimes hard. And so what you've been given is several tests that decide whether things converge. So there are tests. There are tests you can do to decide whether it converges. And when I say test, that means a calculation you can calculate and it will tell you whether it converges or not. Okay, and even worse, it could be that this is also a function of x, and different x's, when you sub them in, will make different series, and some of those series will converge and some of them won't, depending on the value of x. That's called power series. So it may be that what you have is something like this. And this is called a power series. And different x make it converge or not. Yeah. And then the goal is not just to say, does it converge, but to say which x's make it converge and which x's don't. Yeah. And so the collection of x's that makes that converge are called the interval of convergence. That's bad. I'm just going to rub that out. Rather than the interval of convergence. So they are the x's that if you subbed it in and then looked at what the series turned out to be after you've subbed it in, then it would converge. That's what the interval of convergence is. So that's the idea. So the big idea is that we can make these things, we can decide whether they converge or not. And sometimes we have to decide based on what the value of some unknown number in the formula is. So it's really best to do an example. But I will say the names of the three of the tests you've got. There is one test that in some textbooks is called the test for divergence, and in some textbooks is called the necessary condition for convergence. I believe that's what it's called in your course. And that's what I said earlier. If you have a sum, it doesn't matter where it starts. This cannot possibly converge if the individual terms don't go to zero. So if you remove the sum and just think about the list of the last term, does that get closer to zero? And if so, it has a chance of converging, but it still might not. So if the limit as n goes to infinity of an is not zero, then the series does not converge. But if the limit is zero, you have no idea. It still might converge, it might not. If the limit So if that limit comes out to zero, you don't know if it converges or not. But if it doesn't come out to zero, then you are absolutely certain that it does not converge. Yeah, that's the test for divergence. And it's the first thing you should check. If you are given a random series, you should check that first. And then the next rule is the alternating series test. And that only works if you have an alternating series. And an alternating series, the terms switch back and forth between positive and negative. So in an alternating series, it'll actually be minus 1 to the n times something. So somewhere in that a to the n, there will be a minus 1 to the power of n. And what that will mean is that the terms switch back and forth between positive and negative, because minus 1 to an odd number will be -1, and minus 1 to an even number will be +1. And so it has to be able to be written this way. And then if these get smaller, then it'll converge. So if at some n, this bn is greater than bn plus 1, which is greater than bn plus 2 forever, it's decreasing, then the series converges. So you just have to be sure that at some point, it doesn't have to be right at the beginning, but it might be later on. At some point, from that point forward, every term is smaller than the one before. Yeah. I will say that this bn is supposed to be positive because all the negativeness is in this minus 1 to the n. So that's the absolute value of this. So En is the absolute value of An. So that's, yeah. So there are some very classic examples of alternating series that don't converge, and they tend to be the ones that this sequence of BNs always goes up and down. If it keeps going up and down forever, then it probably won't converge. As long as it actually goes to zero, then you'll be okay. That's the alternating series test. Only applies to alternating series. And you'd think, why would you care about only alternating series? It's just that they do come up rather often, surprisingly. And then the final one is the ratio test. Now, there are, in fact, a couple of other ones that are mentioned during the assignments or in passing in the notes. There's one where you compare it to an integral, and there's one where you compare it to another series which you know converges, but they're not formally examinable. Yeah. So there's the ratio test, and the ratio test says you start with your series. There is no restrictions on whether it's an alternating series or not. You're allowed to use it for alternating series or otherwise. And what you do is that you do this step. You calculate An plus 1 divided by An. And then you do the limit of the absolute value of that as n goes to infinity. And this will come out to an answer, which I shall call L. And then if that limit is more than 1, then it definitely does not converge. Some people call that diverging. If that limit is less than 1, then it definitely converges. And if that limit is equal to 1, then you still don't know. L is less than 1, converge. L is equal to 1, don't know. And L is greater than 1, diverge, or does not converge. Yep, that's it. So if this limit doesn't exist, then you don't know. Yeah, that's it. They are the tests. The ratio test is the most powerful one. It will work for anything. Well, I mean, it might still be really hard, but it's very useful for things that have a factorial in them, and things that have a power in them. So if you have those in your expression for An, then the ratio test will be really useful. Feel free to come in if you want. Looking for Maths 1B revision seminar? Yep. Okay. So that's what series are. And what we should do is do some examples that are difficult, so that you can see how to deal with anything. There is something that isn't counted as a test. These are the tests. Before that, there's the I recognize it, and so I know it converges. So these don't count as tests. They're not listed as tests, but they are in your course. Just note that test 0 there's some classic series. That some of them the tests won't work for, but you're just allowed to know that they don't converge or do converge. So the classic series is the harmonic series. And that does not converge. So the individual terms, they do go to 0, but it still doesn't converge anyway. So this is the classic answer to why this one says if the limit of the individual terms doesn't go to zero, you don't know, because the harmonic series, the terms go to zero, but it still doesn't converge. Like, even though you're adding a smaller fraction every time, you can just get it to be as big as you want. It just takes a long, long time. So that's the classic. And there's also a P series, which is things like 1 over n squared, or 1 over n to the half, or 1 over n to the, 5 over 3, or whatever, 1 over n to the p. If you have something that looks like that, there's a specific number in each of these spots. Then if p is more than 1, it will converge. And if p is less than or equal to 1, it will not converge. And something like this will fail the ratio test. Like if you do the ratio test on something that looks like this, it will give you the limit is equal to 1. And so you can't use the ratio test on something that looks like this. And you can't use the alternating series test because it's not an alternating series. And you can't use the testified divergence because the terms do go to zero, and so that doesn't tell you anything. And so the tests kind of don't work for p-series, and so they've separately just told you how to tell if a p-series converges or not. So it's useful. And this, in fact, will imply, they don't tell you this, but it does, in fact, apply for anything that has a polynomial on the bottom. And even something that has a polynomial on the top and on the bottom, as long as the highest exponent on the bottom is at least 1 more than the highest exponent on the top, then it will converge. So anyway, but they wouldn't give you one that was that in that zone in an exam because they haven't explicitly taught you that. So, but just thought I should let you know. But yeah, the ratio test will fail for anything that has a polynomial in n on the top and the bottom. So yeah. So these are the classic series, and there's one more classic series that you should know about that doesn't happen at the early part when you're talking about series, but happens later when you're talking about Taylor series. And it is the, oh no, it does happen, just a second. Wait. Geometric. The geometric series, like that. So the difference between this one and this one is that this one has the n in the base, this one has the n in the exponent. And so there will be a number in that spot. So these geometric series have like a half to the n, n equals 0 to infinity, like minus 3/5 to the n. And you can have numbers in those spots. And basically what happens is that if this number is less than 1, then it'll converge. So in fact, even if it's the absolute value is less than 1, then it will converge. And if this is greater than or equal to 1, then it does not converge. But I will say this is one of the only series that we know what the actual sum is. The actual sum is equal to 1 over 1 minus x. But only if you start at 0. Then it will come out to this answer. There are very few series that we know what the answer is going to be for what it actually adds up to, and this is one of them. Yeah. And there's one more series that we know what it adds up to, which is this one. This one here. This will always converge no matter what x is. And the answer is e to the power of x. Cool. Now, I will say that the ratio test does in fact work on both of these. It's kind of designed to deal with things that have factorials and powers. That's what the ratio test is designed for, and it will work. The ratio test will work on those. But what the ratio test won't do is tell you what the total sum is. These ones are the ones that we know the total sum for. Okay, just needed to mention those because they do come up. So if some maths lecturer gives you a question that says, what is the value of this series, as in what is the sum, then it must be one of these two, or you wouldn't know. Because these are the only two that they've told you what the total value is. Unless they have separately made you calculate a Taylor series for something, and then it might be that one. But these are the two. So if they just randomly give you one that says, what's the total? That's what it is. Now, you had one that says, what's the total, didn't you? Yep. So I am going to do something similar to that one. Is that from the practice exam? Okay, I'll do one that's similar but not the same. Because some people want to keep practicing now, but practicing for time. Yeah. Oh, the one like that. Okay, so here we go. Let's do some examples. This one, is that anyone got any questions about this at this time? Okay. There we go. Find the value of this. So the fact that we can find the value means that it must be either a geometric series or a Maclaurin series. A Maclaurin series is also a Taylor series, but it must be a geometric series or a Maclaurin series that we're familiar with. And it doesn't have any factorials in it, so that means it's a geometric series. So that's my thinking on that. So this is my thinking. Since we can find the value, must be geometric or e to the x that's involved somehow. And there's no n factorials, so it must be geometric. That's my thinking about my decision-making process about what I'm going to do. So since it must be a geometric series, there's no point in doing the ratio test because we know exactly when geometric series converge, and they've implied that it does converge, so we don't by asking us to find the value. So if it didn't converge, we couldn't find the value. So there's no point deciding whether it converges. What we should do is just try and find the value. And the only way to find the value is to write it like this. Has to be written as single thing to the power of n. That's what we need to do. Okay, so that's our goal. Our goal is, this is what I'm thinking, our goal is something to the power of n. So I'm looking at this and I'm thinking, well, if that one wasn't there, then that'd be a little easier because they've both got a power of n. So I'm going to do this. I may just fiddle around with this for a bit before I do the sum. So 3 to the n plus 1 on 2 to the 2n. No, I won't. Bear with me. I'm just going to do it properly. So what I would like is things to the power of n. So I've removed this plus 1 by saying, well, 3 to the power of n plus 1 is the same as 3 to the 1 times 3 to the n. And 2 to the power of 2n is 2 squared to the power of n. Okay, that's where I am. And so what I'm going to do is I'm going to move this 3 out the front of the sum because it doesn't involve an n. And then this 3 on 4 is this, because that's one of the things about how powers work. When you do powers on top and bottom of a fraction, I can do the fraction first. And now this is in the right format. And look at that, 3/4 is less than 1, and so yes, it will converge. The problem is that my formula for what a geometric series adds to starts at 0, not at 2. And that's a problem. So I need to now, so if at this point I can tell it converges. 3/4 is less than 1, so it definitely converges. Geometric series, 3/4 is less than 1, so it definitely converges. So that's true at this point. If all they asked to say, does this converge, I could stop there. I could have done the ratio test as well. That would have worked too. But if I want to know what the total is, I'm going to have to make it start at 0. So here's my plan. If I would like that to say 0 there, then I'm going to bump this up by 2. I'm going to subtract 2 from all of these numbers and add 2 here so that it works out to the same total overall. Just let me check. When I sub n equals 0 into this, I get 3/4 to the power of 2. And when I sub n equals 2 into this, I get 3/4 to the power of 2. When I sub n equals 1 into this, I get 3/4 to the power of 3. When I sub n equals 3 into this, I get 3/4 to the power of 3. So if I sub all of these numbers into here, I get the same answers as when I sub these numbers into here. They are the same sum. And so that move that I've made, where I made all these go down by 2 and all these go up by 2, it's called shifting the index, in case you're wondering. So now I'm going to do the thing that I did before and separate out that power of 2. Like that. And so that's 3 times 3/4 squared. Okay, now it starts at 0. Now I can use the formula. Like that. So that's how the formula works. The sum from n equals 0 to infinity of x to the power of n is 1 over 1 minus x. That's a times there, by the way. So n equals 0 to infinity, x to the n is 1 over 1 minus x. That's the formula I'm using. And so now I've got an answer. If I multiply this and this by 4, I will get that. And so they cancel, and I've got 12 lots of 3/4 squared, I guess. You can probably leave it like that if you're in an exam, but I feel uncomfortable, so I'm just going to. 27/4, apparently. So like 6 and a bit. Just actually 6 3/4. So cool. And if you really, really wanted to check that, you could actually try adding up several of them. So 3 to the power of 1 divided by 2 to the power of 2 plus 3 to the power of 2 divided by 2 to the power of 4. Now it's going to take me forever. Anyway, you could actually just do a whole lot of them and see that it comes close. Some calculators allow you to do sums, not infinite sums. Does yours do infinite sums? But that's why you're not allowed to have that kind of calculator in this exam. Yeah, Desmos allows you to do infinite sums as well. Not that version of Desmos, but the online Desmos calculator can do that too. And it's just approximating it. It'll give you a decimal answer. But it did come out to 6.75. Okay. Cool. So that's that. So really important to look at it. And if they ask you to find the value, then this is pretty much what you're going to be doing. And there's a lot of little tricks that I've used there that you can reuse. Yeah. If they're very nice to you, they'll make it start at 1, start at 0 to begin with. But, you know, no way of controlling. Okay. So, do I want that? No, I do not. Just a second. I'm just going to switch these two. Wait. Bear with me. No, let's do it. I may try and make it better later. For which x does this converge? So I'm just going to say this is the same as asking what's the interval of convergence. It's not a geometric series. It does have an x power of n, but it's got this factorial in it. And it's not a straight up e to the n. Like if it was this, then we're only off by a little bit for my e to the n, e to the x. So that would have, I could have dealt with that. So I'm going to have to, well, and things with powers and factorials are, that's what the ratio test is useful for. So I'll use the ratio test. So I'll say AN is this entire thing. And then AN plus 1 is the thing with n plus 1 everywhere there's an n. Like that. And then the ratio test requires me to do AN plus 1 divided by AN. I've just done that 1 plus 1 and replaced it with a 2. And when I divide by AN, that's the same as putting it up the other way and multiplying instead, because that's how fractions work. And then what I need to do is figure out the limit of this. And the quickest way of dealing with this is to put all the things that are similar to each other together. So I've got an n plus 1 squared over an n squared. I've got an n plus 1 factorial over an n plus 2 factorial. I have an x to the n plus 1 over an x to the n. And I can do that because multiplying the tops and multiplying the bottoms is how fraction multiplication works. So this is the same as this because it's multiplying the top, multiplying the bottoms. Okay. So for this last one, that is just x. X to the n plus 1 divided by x to the n is x. And for this one, well, n plus 2 factorial is n plus 2 times n plus 1 times all the things all the way down to 1. And this bit here is n plus 1 factorial. And so n plus 2 factorial divided by n plus 1 factorial must be n plus 2. And so what I get here is 1 over n plus 2. Because I've cancelled out an n plus 1 from the top and bottom. N plus 1 factorial from the top and bottom. So what I've done is I've replaced the n plus 2 factorial with n plus 2 times n plus 1 factorial and then cancelled the n plus 1 factorial. And this one, I'm going to write it like this. So because they're both squared, I can bring the squared out. And this is 1 plus 1 over n. Okay. So the limit as n goes to infinity of the absolute value of an plus 1 over an is the limit as n goes to infinity of 1 plus 1 on n squared, 1 on n plus 2 absolute value of x. So I can do the absolute value of each bit separately, but all of these things are positive anyway, and so only the last one needs an absolute value. And this limit is 1. Because the limit as n goes to infinity of that is 0. So I've got 1 plus 0 squared times 1 over times 0 times absolute value of x, and that is 0. And the question of whether it converges is the same question as, is this number less than 1? And this number is less than 1 no matter what x is. So less than 1 for any x. So it converges for any x. Which seems like a disappointing answer. Like, for which x does it converge? The answer is it converges for any x. That happens. The only time you'll get it converging for any x is if this answer comes out to 0. Because if this answer comes out to like even 0.1, then the x's that are less, that are like, yeah, if this came out to, no, maybe not 0. If this came out to a pure number that had no x's in it, and that number was less than 1, then it would always converge. But usually you get not 0 times the absolute value of x. So I'm just going to do a what if. Okay, let's do a new question. My new question is, what if that n plus 1 factorial wasn't there? I'm going to just do this. I'm going to make one change to this. And there's no factorials this time. Okay. So my an plus 1 over an, I'm going to try and do it in one go. N plus 1 squared x to the n plus 1 over n plus 1 plus 1 times. Okay. I've got n plus 1 squared to n squared times n plus 1 over n plus 2 times x to the n plus 1 over x to the n. And so I've got my n plus 1 over n all squared. And this one here, I'm going to divide top and bottom by n. So that's 1 plus 1 over n and 1 plus 2 over n, like that. And so the limit as n goes to infinity of the absolute value of an plus 1 over an is the limit as n goes to infinity of 1 plus 1 over n squared, 1 plus 1 over n over 1 plus 2 over n times the absolute value of x. And so we get 1 plus 0 squared times 1 plus 0 over 1 plus 0 times the absolute value of x, which is just the absolute value of x. And this will only, the original series will only converge if that answer is less than 1. Which means that the x will have to be between -1 and +1. So I will say, so this is saying that the distance between x and 0 is less than 1, and so it has to be between -1 and +1. I will say, technically, what if the x was exactly equal to 1? In that case, when I ran through this process, this would have come out to exactly equal to 1, and the ratio test doesn't tell you anything when the answer comes out to 1. And so technically, I in fact do not know whether it converges when x is 1 or whether it converges when x is -1, and I'm going to have to check them separately. So check x equals -1 and x equals 1 separately. And the ratio test won't work for those. So the only way to check is to put it all the way back into the original series and make a decision based on what it looks like. So when x equals 1, -1, like that. That's an alternating series because of the -1 to the n. And an alternating series will converge when the individual terms get smaller, but the individual terms are getting bigger. N squared on n plus 1 doesn't go to 0. There's like 16 on 5, and then you've got like when n is 100, it's like 1,000,000 on 100. What? Pardon me, 101. That's a huge, huge number. That only increases. So n squared on n plus 1 goes to infinity as n goes to infinity, so it diverges, does not converge. And the same thing will happen when x is 1. Oop, 1 to the power of n. Because 1 to the power of n is the same as 1. So, yep, neither of them converge. So actually, so yes, converges exactly when x is between 1 and -1. And not when x is -1 and not when x is 1. You ready? I have one more. I'm going to change this in one more way and see what would have happened. That way, up. What if the fraction was not n squared divided by n plus 1, but the other way up? Then the ratio test would still have come out to absolute value of x. So when you do the ratio test, the limit then goes to infinity of an plus 1 over an. I'm going to skip that working, and it's still going to come out to the same answer. And so you'd still get converge when that is less than 1, which is between here. You would still get that answer. But this time, when x equals -1, the original sum now the individual terms do go to 0. Right? And so it will in fact converge. So now n plus 1 over n squared is decreasing as n increases. Each one is smaller than the one before. So now, and therefore, it converges by the alternating series tests. Yep. I mean, it might increase temporarily. Like when n is 2, you get, like when n is 1, not that n is 1 is a matter, but if n is 1, you get 2 over 1. And when n is 2, you get 3 over 2. No, it has decreased. Okay, it's decreasing always. So some of them increase for a bit and then decrease later, but as long as it decreases eventually. And when x is equal to 1, that one will diverge because that's 1 plus 1 over n squared. No, 1 on n plus 1 on n squared. Yep. That's okay, isn't it? Yeah, n divided by n squared is 1 on n. Right. And the 1 on n part, that's the harmonic series and that diverges. So, yeah. It's harmonic. There you go. That's how it goes. So if a piece of it is the harmonic series, then it will diverge. And so actually it converges exactly when minus 1 is less than or equal to x. Because it converged when x was minus 1, but it didn't when x is 1. All right, it's time to ask a question if you've got one. I use minus 1 and 1 because they were these numbers here. It is not always using minus 1 or 1. Very important question to say, is it always in a maths course? If it had been that one, for example, then when I did the ratio test, I would have gotten there'd be like a, no, can I do, there would have been a 2 to the n plus 1 over 2 to the n in there. Something like that. Yeah. And that would have come out to 1 and 1, and that would be a 2. That would have come out to 2, would have come out to this. And we need 2 absolute value of x to be less than 1. And so x is less than a half this time. And so x would be between minus a half and plus a half. And then what I would do is I would test x equals minus a half, and I'd get n equals 3 to infinity n squared 2 to the n minus a half to the n. And so that would be n squared. And the 2 to the n and the 2 to the n on the bottom would cancel each other out, and I'd get a minus 1 to the n. And so that one converge. Yeah. And the other one would diverge. And so you'd end up with the x equals plus a half diverge. And so you'd get that. Cool. And you'll see that in general, the fraction has to cancel out the power of a plain number that's there. So, yeah, so that's how they work. And if you trust your algebra, you'll be okay. because sometimes they have like, 3x power of n, or they'll have x to the power of 2n. It'll all work out. Just trust your algebra, and you can figure it out. Yeah, and that's pretty much it. That's how the ratio test works. You can do the ratio test when there's an x or when there's not an x. And when there's an x, they usually want you to figure out exactly which x's make it converge, which is called the interval of convergence. Yeah. I will say the radius of convergence is how far it is from the center of this to the edge. So in this case, the radius of convergence is a half. Yeah. But it is totally possible. One last, I won't do the example. I'll do this exact one, change it one more time. Like that, x minus 3 to the n. Then what would have happened is it would have been, everything would be exactly the same, except you would have gotten 2 of the absolute value of x minus 3 is less than 1 instead of x. So back here we had an x in this spot, and I've put x minus 3 instead. It would have come down to here, and you would have gotten x minus 3 is less than a half. And so this is saying the distance between x and 3 is less than a half. So this is the radius here still. So the imagining we have here is 3, and we've gone up a half and down a half from there. Yeah. Because that's what this is saying. That the center is 3 and the radius is half. And so we would have ended up with x between 2.5 and 3.5. Those mathematicians don't like mixed numbers, so they probably prefer 5 halves and 7 halves, whatever. And it will work out to have an or equal to, because we haven't changed anything other than where the middle is, so the same reasoning would still work. Because when you sub in 2.5 into here, you'll get 2.5 minus 3, which is minus a half, and now it's the same calculation. Yeah. So there you go. That's how intervals of convergence work. One thing I like about the way I've done this, I don't know if you like it, I like trying to make up examples by just changing one of the ones I've got just a little bit to see how it makes a difference. Because it's much easier to see the decisions that are made by comparing two questions that are really similar to each other. So it's something that you can do while you're studying. And if you're not sure how to cope with it when you do it, then that's what the Learning Centre is for. You can come and talk to us about it. Yeah. This goes till 11, right? Yeah. I can go a little longer if we're still talking about things. Happy with our series at the moment? Any more questions about series? Cool. Well, the only other thing on my list from that was written on the Maths Learning Centre wall was determinants. Is determinants in Maths 1A as well? Or is it only in Maths 1B? It was back in Maths 1A. What do we use determinants for in Maths 1B? That must be for eigen things. Oh, yeah. There is a determinant in partial derivatives too. Just a second. I'm just going to say this. So determinants turn up definitely in multivariable calculus, right? Where you do the second derivative test with the they turn in multivariable calculus, and that's where you've got like fxx, fxy, fxy, or fyx, and fyy, that thing, right? And that has to come out to positive or negative or whatever. Okay. And they turn up in eigenvalues, right? I think that's it. They probably turn up when you're doing, do they turn up when you do orthogonal diagonalization? No, because that's eigenvalues anyway. Okay. They used to turn up when you did rotation matrices, and you could tell that a matrix was a rotation when its determinant came out to exactly 1. That's not a thing anymore? I don't think it is. Okay, just checking. Okay. No, that's it. So that's when they turn up. So since the person who asked this on my wall isn't here, I can't ask them what they meant, but I can say that they do turn up in these places. And the determinant of a 2 by 2 matrix is determinant of a 2 by 2 is those two minus those two. Yep. And the determinant of a bigger matrix is made by turning them into smaller matrices. So when you do the determinant of some random numbers, seem to be favoring 2s today. So when you do the determinant of a big matrix, what you have to do is you have to pick a row or a column and take those numbers and put them next to some smaller matrices. And it doesn't matter which row or column you pick, but you can always pick the one that has the most zeros in it. That's usually the best plan. And you have to put pluses and minuses next to these numbers as well. And you choose that based on the fact that the correct pluses and minuses in the top left corner of the matrix you're currently thinking of, there's always a plus. And then every time you switch positions, it will switch to the opposite one. So this one will be plus, minus, plus, minus. You go plus, minus, plus, minus, plus. And so they're the numbers we want. Minus 0, plus 7, minus 0, plus 2. It doesn't matter what this one is because we're going to times it by 0 anyway. It doesn't matter what this one is because we're going to times it by 0 anyway. But what the matrix is that goes in those spots is the matrix you get by removing this column that we just thought about and the matching row. So this one would be minus 6, 2, 1, 3, 5, 8, 2, 0, minus 8. And this one would be 3, 5, 7, 3, 5, 8, 2, 0, minus 8. And this one, I'm going to skip that one. And this one would be 3, 5, 7, minus 6, 2, 1, and 3, 5, 8. And then you would do the same thing for each of these ones. And so this one here, for example, you could pick the third row, for example, not that I need it. I don't need those ones. This one I could pick the third row, so I'll have 7 times 2, 0, and minus 8. And the correct pluses and minuses are plus, minus, plus, minus, plus. Plus 2, minus 0, and plus minus 8. And then this determinant is 5, 5, 5, 7, and 5, 8, because I removed that one. This one, I don't care what that one is. And this one is 3, 5, 3, 5. And so on. This one would be made of 3 pieces. Yeah, and that's how you calculate a determinant. The thing is that when you're doing eigenvalues, you're not just doing it with numbers, you're doing it with lambdas. And so you're simultaneously doing eigenvalues and matrices. Oh, sorry, and algebra. And the goal at the end is to factorize what you get. And so what you should do is try and factorize as early as possible. And so there is another rule about how matrices determinants work, which is that if you do row operations on the matrix, then some row operations won't change the determinant. And also, if I see all these are even numbers here, if I factorized out a 2 out of that row, it would multiply the determinant by 2. So there's this thing I could have done right at the beginning to make it simpler for myself. Bear with me. Okay. Okay. Do I want that one? Wait. Okay. This is my matrix. So if I want the eigenvalues, so the eigenvalues, which I write as just e-values, I need to solve lambda I minus a equals 0. That's what I need to solve. And so the determinant of lambda I minus a is this. And so since there is a row that's mostly zeros, I could expand along that row if I wanted. It's totally a thing I could do. But I could also, if I wanted to, factorize out this lambda minus 3. So I wanted to do that as well. But I will choose to do this. This is this row, which is plus, minus, plus, minus. So this will be plus lambda minus 3 times the matrix that's left behind, like that. And now it's an ordinary lambda minus 2, lambda minus 4, minus. Not a fan, people. So I would recommend at this stage, do not expand this out because the whole point is to factorize it anyway. So just leave this here. So I already know that one of the eigenvalues is 3 to begin with, and then I have to factorize this, which is not pretty. So you probably have to expand it and then factorize it. But if you're if you concentrate very hard, you can sometimes do fun things, but I choose not to. Oh, that's bad. Sorry, everyone. It's not going to have fun eigenvalues. I really thought I made one with the right number. Oh, no, that should work. What have I done wrong, people? Oh, yep, you're right. That's much better. Thank you. And now I think of things that multiply to give minus 3 and add to give minus 6, which is not going to be fun either, but that's okay. Have I done that right too? Uh, that's what the quadratic formula is for, people. So I just leave it like that and then solve to figure them out. The reason I'm distressed is because if I multiply this matrix by this vector, I get 2 plus 0 minus 5, which is -3. Oh, David. Okay, that's why. I set it up wrong. I'll get 0 and I'll get -3. I set it up so that it would do this, but that is not a multiple of that. It's -3 times this would have a +3 there. Should have put a -2 just here. That would have made it all work nicely. Okay, that's all right. It's very hard to on the fly come up with matrices that have eigenvalues that you can whole number eigenvalues. Okay. All right, sorry, that was just me worrying about things. Okay, but anyway, that's a point there. And you can also, if you really want to, you can also, if you really want to, sometimes you get matrices that have just bear with me. This one should, nope, 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 nope. Ignore that entirely. Right. So this one's not nearly so easy. I can't just go along one of the rows because there's not so many zeros. Or in fact, there's no zeros. But what you can do is row operations if you want. So I know that if I add row 3 onto row 1, I will make a 0. And so I can start thinking about doing those things. I can at least make one more 0, and that will make it easier. So do a row operation before I do it. And any row operation where you add one row onto another row will always produce, doesn't change the determinant. So you can always do that. Yeah, but it sometimes doesn't help. You can even do column operations if you want, and it'll work fine. So, yeah, that is a thing that you can do. So I could do row 3 is row 3 plus row 1, and that won't change the determinant. So when I added row 3 onto row 1, I got this. So lambda minus 2 plus another -1 is lambda minus 3. This plus this is 0. Minus 5 plus lambda plus 2 is lambda minus 3. And what I can do is I can factorize out the lambda minus 3 out of that row. And so there's definitely a lambda minus 3 that's going to happen. So there are two moves that you can make. You can make row operations like this and it won't change the determinant. And you can factorize out a common factor out of the entire row and leave behind whatever's there. And they are moves that you can make when doing row operations. And then look at this. I can do row 2 is row 2 plus 4 lots of row 3. And that will produce zeros in these spots here. Oops, sorry, where to go? That will produce zeros here because I'll add on them. And so I get the zeros that I was looking for. And now I can expand along that middle row. And it'll be great. Oh, look at that. It turned out so nice in the end. And so I've got lambda minus 3. We'll expand along the middle row. And so that'll be a plus, minus, plus. So we'll get minus lambda plus 1 times lambda minus 3, 1, 1 minus 5. That's interesting. Oh, wait. That's not a plus. Plus, minus, plus, minus. Sorry. No minus there. I made the classic mistake of starting with plus here, but you have to start plus there. And then when I switch to that one, it's minus. Okay. And so now in this one, I've got lambda minus 3 times 1 minus 1 times minus 5. And I've got lambda minus 3, lambda plus 1, and lambda minus 3 is 5, lambda minus 3, lambda plus 1, lambda plus 2. So my eigenvalues are 3 and minus 1 and minus 2. Isn't that cool? That's very pleasant. So those moves that we made where we do row operations to make a 0 and sometimes factorize things out and row operations to make more zeros can slow and really make that process quicker, and it will factorize stuff for you along the way, which I really like. I hope that's helpful. And if you're watching this online and you were the person who wrote determinants on the whiteboard, I hope it's helpful to you as well. Okay. Well, that is the 11 o'clock, but I will ask you, did you have anything in particular you were hoping for? Yes. That is for the example. Yes, you can assume these are going to be the same. It's extremely hard to think of a function that for which this isn't true, because the only way to set up a function where they are different is to have one of those things that have different formulas in different places, and they're not going to do that to you. So, yeah, if you have a function that has just a single formula that's made of polynomials and functions you're familiar with, it's guaranteed to do this. So yeah, absolutely true that that you do not have to worry about them being calculated separately. Even in second year multivariable calculus, they don't do that to you. So yeah. All right. Cool. Just bear with me. I really want to check something with this because I feel like I've made another mistake in here. So I just want to check that before the video gets turned off. So if the eigenvalues really are 3 and minus 1 and minus 2, then the diagonal should add up to 0, which it does not. So I've done something wrong. So bear with me. I'm just going to go back and look at my row operations and make sure I didn't copy anything wrong from one line to the next. So we had lambda minus 2, minus 5, 4 minus 1, 4, 1. That's a plus 2. And so when I added this onto there, that gave me a minus 3, 0, and a minus 3. And I pulled out the lambda minus 3 and left me with a 1. And I added that onto there. Ah, there it is. That's a 2. That there is supposed to be a 2, not a 3. Yep. Lambda minus 2, lambda minus 2. So this is a lambda minus 2. 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 And that makes that a lambda plus 3. Makes it a minus 3. So 3 plus 1 minus 3 minus 1 minus 3 is -1. And when I add up these, I also get -1. Okay, so I'm feeling better. The eigenvalues should add up to the same as the diagonal, and so I was worried, but I couldn't see where my mistake was, and it was because I copied a 2 down on this line and wrote it as a 3 on this line. Wow. Normally my mistakes is making a minus into a plus, but today it was that. So, okay, example fixed. I feel better now. I will stop the recording properly now.